Okay, so it's my pleasure to introduce Adam Sheffer talking about geometric incidences and the polynomial method.
Thank you. And thanks for having me here. Pleasure to be here. First thing I want to say, I understand that I heard that I shouldn't say this, but feel free to participate. I like it when people say comments. I understand I don't even need to say it here. If you have anything, just comments, questions, whatever, just stop me at any moment. And today I'm going to talk about a family of problems called incidence problems. It's a field of combinatorial problems, but in a sense my goal today is actually to show you that they're related to a lot of other parts of math. In this talk I want to show you that while it's combinatorial, it also has interesting connection to many things. Okay, let me just start. I'm going to survey it, try to convince you why it's interesting a bit, and try to show you some proofs using different rules. And I'm going to start by defining what's an incidence problem. So what is an incidence problem? Let's start with a very simple method, a very simple problem, one of the simplest incidence problems. We're in a plane, we have some points, we have some lines, and an incidence is a pair of a point and a line such that the point is on the line. So let's say here we have 3 incidences because it's on 3 lines, and if you'll count, we have in total 15 incidences here. Okay, you see what the definition is of an incidence? Okay, now one well-known result in the combinatorial geometry is the symmetry theorem, and it tells us that the number of incidences between m points and n lines is at most this expression, m to the 2/3, n to the 2/3 plus m plus n. Okay, first thing, we can really ignore these terms. They usually don't dominate the bound unless the number of points is really much larger than the number of lines or vice versa. So this is the bound that's interesting to us. And this is tight. There are configurations of points and lines that can get to this number of incidences. I'm not going to say the full details, but for example, you can take a thin and tall section of the integer lattice and take a lot of lines that pass through one point in each column, and you can get this for any range of m and n. Okay, so this problem is solved. Why am I going to serve it today? It's just one example, one of maybe the simplest example of a big family of problems. So we can talk about incidences between points and circles, or incidences between points and parabola. Already these two are open, long-standing problems. No one knows how to handle this. And it goes further. We can talk about incidences in higher dimensions. Maybe in a d-dimensional space and we have some hypersurfaces. Maybe in a complex space over finite fields, there are really a lot of variants of these problems. And if you're seeing this now for the first time, let me say, in all of these problems, the point is we have points and we have some sort of objects, and we want to figure out what's the maximum number of incidences that we can have between the points and the objects. That's the common thing. And you might think, okay, Adam, you have this family of problems, you have 1,000,000 of those, but why do we care? Why do we need all of these problems? So as I said, I want to focus today on connections to all sorts of other fields. And this is one way to do it. And incidences pop up in a lot of places, a lot of surprising places. There are a lot of problems that can be reduced to an incidence problem. Let's do some name dropping. So from indiscrete geometry itself, maybe the largest result in the past decade is the Guthka's distinct distances problem, or solution to the distinct distances problem. And this was done by reducing the problem to a point line incidence problem in 3-dimensional space and solving it. Brook and Demeter, they have all sorts of papers where they use incidences for discrete restriction problems. There's a paper from a few years ago by Bombieri and Bourgain where they call it number theory. It's about studying some sort of energy of the Gaussian numbers. I hope you're not going to ask too many questions about this one because I'm not too much of an expert on it. And people study expanding polynomials using incidences, and I had an urge to put a second name dropping slide. So if you know some additive combinatorics, it's very common in additive combinatorics. I guess the main book of additive combinatorics is the one by Kao and Vu, and they have a whole chapter about how to use incidences there. There's a whole group of people from around New Jersey that study all sorts of coding theory problems, theoretical computer science using incidences. It's been used to study minors of totally positive matrices, and the list just keeps going and going. Somehow incidences pop up in a lot of different places, a lot of times in places where you really don't expect to see anything that looks like an incidence. My personal belief is that the reason is that these are some sort of basic mathematical object, and that's why it has so many connections, but I guess we're going to see it in the next few years if this keeps happening or not. Okay. But this is just name dropping. I'm not telling you anything. So I thought I should show at least one example of how incidences pop up in a place that doesn't really seem remotely close to incidences at first. I can't show anything too sophisticated because I don't have a lot of time, but I chose this example from additive combinatorics. It will take me 2 slides to get to the problem. If we have a set of real, let's say that A is a set of n real numbers, the sum set of A is just all the sums of pairs of elements from A. You take every 2 elements from A, you write their sum. Now, if A is this random set, you took n real numbers at random, you expect the sums not to really repeat, and you have a sum set of about n squared, different sums. But there are sets that have a much smaller sum set. They somehow have some additive structure, so they have only a few sets. You can guess. For example, the set of 1 to 3 up to n, you can very easily check that the number of sums, distinct sums, is 2n minus 1. And this is true for any arithmetic progression, and you can find some other sets with a small sum set. Okay, so most sets have a very large sum set, some have some sort of structure that gives them a small sum set. Okay, we can say the same thing with product sets. Product set, all the set of products of pairs of elements from A. Really the same definition. And again, take a random set, you really expect it to have about n square elements, but there are sets with some sort of multiplicative structure that will give them only about n elements in them. You can guess on your own what sets, right? So before we had arithmetic progressions, now you can take a geometric progression and you can very easily verify that the number of products in it is very small. Where is this going? The sum-product question asks, is there a set that has both a nice additive structure and at the same time a nice multiplicative structure? Can this happen? Can both of these be small? And first, of course, it depends what do we mean by small, right? How small do we want it to be? So the conjecture is this shouldn't exist for any definition that you like of small. Here's the original conjecture of Erdős and Severely. And what they said, basically, for any epsilon as small as you like, take any sufficiently large set, and either the sum set or the product set would be very close to the maximum. A to the 2 minus epsilon. Oh, I should say, omega notation, if you're not familiar with it, is just the opposite of sum. It's opposite of O notation. It means that this is at least some constant times what we have here. So this says that there's always something very close to the maximum, very close to A squared, either the sum set or the product set. But it's a conjecture, we don't know. We're very far from it. It has a lot of other variants, but I'll focus on this one. In 2009, Shimoshi showed that every set has a sum set or a product set of at least A to the 4 thirds. The star in the omega notation just means I'm hiding some polylogarithmic factors that we don't care about. And very recently it was improved a bit further, but by just 1/2000, something like that. Okay, so you can see we're still very far from knowing the correct answer here. This is really far from 2. What I want to show you very briefly now is how to prove this sum bound and order bound by Elekes using incidences. So I should say, when first this problem arose, it was stated for integers, not for real numbers. And it was mostly studied by more number theory-oriented people. And there were several relatively small progresses on it, of A to the 1 plus epsilon of all sorts. And then Elekes' result was, in a sense, the big breakthrough. Suddenly there was a much larger bound, and it was very simple. If you think of this problem geometrically, you can in a very simple argument, get to a much stronger bound than was known before. So how did incidence get to how are incidence related to this? It looks like a number theory problem. Here's what we can do. Take a set of, we have a set of n real numbers. We're going to use it to define a set of points and a set of lines. The set of points is going to be all the points with an x coordinate from the subset and the y coordinate from the product set. So it's a Cartesian product of the subset and the product set. And a set of lines, so lines are just defined by linear equations. We're seeing they are elements of A. So it's also in some sense a Cartesian product of lines, at least if you look at the equations. All we want to do is count how many incidences are in this configuration. That's all. But we already know how to do this. I told you there's this semi-Trotter bound. It told you that the number of incidences between points and lines is at most the number of points to the 2/3, the number of lines to the 2/3. And we can easily see the sizes of this. The set of lines is obviously a squared, or n squared. Just plug in the numbers, which I'm not going to spend time doing, then you get an upper bound of the number of incidences. We didn't do anything, just apply the incidence bound. But we can also very easily calculate the exact number of incidences. I'm also going to skip the details here, but you can really easily, in 20 seconds, show that each line contains n points, a points. So you can show which points there are. It's very simple. So there are n squared lines, or a squared lines, and each of them contains n points. So in total, the number of incidences is exactly n cubed. And we're done. We proved that the number of incidences is n cubed. And we proved that the number of incidences is at most this expression. Combine them and tidy this up a bit, and you get this result. And this result tells us that either the sum set or the product set is at least n to the 5/4. So you see, by using incidences, we suddenly, surprisingly, got a stronger bound in a very simple way. And this happens in all sorts of places. This is just one example. And in most of these places, it will happen when it's about structure. Like this problem is about additive structure and multiplicative structure of point set of numbers. Usually, when you get to use incidences, it's because there's some element of studying the structure of some set of objects. Okay, so hopefully, maybe I convinced one person or two here that incidences are worth looking at. So let's start to look at them in more detail. What can we say about incidences? The first thing I want to say is there's something called the incidence graph. Now, if you don't like graphs, don't worry. We're not going to do any graph theory. It's just an easy way of representing some of the structure here. We're not, even if you don't know what a graph is, you probably easily see what we're doing. So we have an incidence problem, points and some objects. We're going to define a graph. On one side, there's a vertex for every point, and on the other, there's a vertex for every object, line in this case. And there's a bijection between the edges and the incidences. So if point D is on line C, we'll have point D has an edge to line C. That's all. We just kept some of the information of the problem in this graph. What can we say about this information? So let's imagine that these are really points and lines, like we see in this figure. In this case, the incidence graph will not contain a copy of K22. What is this graph theory notation? It means this. Two vertices on each side, and all of the four possible edges between them. And we claim that this cannot be found in the incidence graph, a copy of this thing. And why is that? That will tell us that we have 2 points and 2 lines, where both lines are incident to both points. But 2 lines intersecting at most 1 point, right? This cannot happen that 2 lines share 2 points. So obviously this does not exist in the incidence graph. Let's try something a bit different. Let's say we have circles. Instead of lines, we have circles. So now we can have K22. We can have 2 points with 2 circles through them. I can have infinitely many circles through 2 points. But we can still say something about the incidence graph. What can we say? We can say that there's no K32. If you take 3 points, it's impossible to have 2 circles that pass through all 3 because, well, 2 circles intersecting at most 2 points. Okay? So we can use this incidence graph to get some structure of the problem, about the problem. And why am I telling you all of this? Because it's an easy way of stating incidence problems. Here's the classical result by Partitioning. If we have m points in the plane and n constant degree polynomial curves, and no KST in the incidence graph, let's make sure we understand what this means. Now, okay, in the incidence graph, it means if you take any S points, you will not find T curves that each of them contains all of the S points. If you take S points, at most T minus one of them will contain all S points. Then you have a bound on the number of incidences. It looks like a complicated bound. It's really isn't. Let's say that we have lines. So lines, we said there's no K2 because two lines intersect at most once. So S is 2. And if you plug in 2 instead of S, you'll get the 2/3 that we saw before, the semi-Trotter bound. So it's a generalization to arbitrary curves in the plane. Algebraic curves, I should say. Okay. And you might... Yes?
So there is no dependence on T in the form of...
Okay, that's a good question. Right, where's T? So T actually will appear as a multiplicative constant here, but we don't care because we think of S and T as small constants, so multiplying by T doesn't really matter. It's not in the exponent like S. It is there. Good point. Okay. You can do the same in the three-dimensional space. Here is a result of Zal, one of my closest collaborators, and he said if we're in R3, we take m points, n surfaces, algebraic, constant degree, no KST in the incidence graph, and some other condition that I really want to skip, we can get a similar looking bound, a bit worse because in 3 dimensions now. And we can keep going. In 4 dimensions, Basu and Sombra, 2 algebraic geometers. So the same, we have hypersurfaces, m points, and hypersurfaces, no KST. This condition we're ignoring, another simple looking bound. Why am I showing you all of these slides? Let's put them together. Plane, R3, R4.
Can I ask a question? Why
Yes.
would you expect that the degree of the polynomials comes in?
Sorry? What? The degree of the polynomial also, it's a very good point. The degree of the polynomial is also hiding here in the constant. Right, it's a good question.
I see.
So it works, if we think of the degree of the polynomial as a constant, it only have small influence on the bound. It's not going to be in the exponents or something like that. Okay, yes, but it's important, of course. Okay, so I will put them all next to each other. And if I'm asking you to find a pattern, you don't need to think, right? It's immediate that there's some specific pattern here that depends on the dimension we're in. And recently we actually did manage to show more or less this result with Fox, Pafsuk, Zal, and myself. M points, n varieties in a d-dimensional space, no KST in the incidence graph, no condition corresponds to the ones we skipped on, and we get, this generalizes the 2, 3, 4 dimensions and actually several other incidence bounds. In a sense, it's one of the most general incidence bounds that we have these days, except that there's this extra epsilon here. There has to be an extra epsilon. You can check epsilon to be as small as you like. Small influence doesn't matter much, but haunts me at nights. Anyway, so I said I want to show you how this relates to all sorts of other parts of math. I hope if I have time I hope to have enough time, let's see, I think I'll have enough time to show you 2 different incidence proofs. One will be...
You could get logarithmic terms to weaken that, or...
Yeah, maybe you can remove it completely, I don't know. Yes, probably could be improved, and you can remove, we already know you can remove it in 2, 3, and 4 dimensions. So it's likely that you can remove it. So I'm going to try to show you a very brief, non-rigorous proof of this, which will be very algebraic, and then I'll show you a different incidence bound, and we're going to see a much more analytic proof for it. 2 different types of proofs. Before I do that, I also wanted to mention another recent result. I managed to show that it's actually tight in several of the main cases. Maybe I'll go back to this slide. So I can show that there's a matching lower bound for incidences in any dimension starting 4, but with no K2T in the incidence graph, only for the case of S equals 2. And it's just one case, but it's the most interesting case. Most of the applications, just like we did with Elekes' Sum-Product bound, use S equals 2, but definitely not all. So this is the most interesting case in a sense. And you might think now, okay, what's a lower bound for an incidence problem? You define some point sets, you define some, I don't know, hyperplanes or whatever we care about, and show that they have a lot of incidences. This used to be the case. Most of the previous proofs work like this. This is very different. It's not so constructive. It actually relies on Fourier transform, probability, some basic number theories. It's quite a complicated bound that I'm not going to talk about today. And it's one of the only cases that we actually get a bound that's nearly tight, except for these annoying epsilons. There's the semi-trotter, this, and maybe a couple of minor cases. Anyway, let's get back to our problem. I didn't tell you how to prove any incidence bound so far, so let's start with the simplest one. Points and lines in the plane. How can we prove an incidence bound? Again, I don't have time, I have to do it very briefly, skip a lot of details, but ask me if you want to know about something specific. So we already know, in the case of lines, there's no K22 in the incidence graph. And the standard, very basic, very easy to show combinatorial result tells you that if you have such a graph with no K22, the number of edges in it is at most m square root of n. You cannot have more than that without having a K22. It's a silly application of hich parts, really nothing complicated. And so because there's a bijection between edges and incidences, it immediately tells us the number of incidences is at most this. But it's bad, it's a bad bound. Think, for example, of the case where m and n are the same. Both of them are the same. So this is n to the 1.5, this is n to the 4th raised. It's not as good. Which is not surprising because we didn't do anything. We just used the fact that there's no K22. I didn't even tell you how. But the only geometry that we used was the fact that two lines intersect at most once. And that's not really special for lines even, right? It's not, or algebraic things even. It's something very general. So how do we use more geometry? There are several ways of using more geometry. I'm going to show you one very specific one today that's using the polynomial method. What's the polynomial method? It's sort of the idea of studying also defining polynomials on our set of objects and studying their properties to solve the problem or to get more understanding of the problem. And in one sense, you can say this. If we have a collection of objects that exhibits extremal behavior, there's often some hidden algebraic structure in it. And we want to study the properties of polynomials to find the structure and use it to solve the problem. So how is this done here? We're going to use something that's called polynomial partition. It tells us the following thing. Let's say we have m points in the d-dimensional space, but we're in the plane really now. You can think of its zero set as some curves in the plane or varieties in space in the general case. And when we throw these out, when we throw, say, these red curves out, the zero set of the polynomial, it partitions the plane or the space into cells, into maximal connected components. Each of them will think of it as a cell. And we're going to say that our polynomial f is an R partitioning polynomial, like in blue there, if no cell contains too many points. What's too many points? If no cell contains more than m, the total number of points, over R to the d. R is from the definition. So it's, I don't know, here we have, I think no cell contains more than 3 points. It doesn't matter what the numbers are, it just matters a good partition is a partition where the cells have bounded number of points in them. And this was originally introduced by Guth and Katz. And they said for any parameter R, any set of points in any d-dimensional space, you can always find an R partitioning polynomial of degree linear, at most linear in R. You can always find a relatively low degree polynomial that the zero set partitions the space into cells, and no cell contains too many points. Okay, that's what they showed. How is this related to incidences? Why do we care about such a polynomial for incidence problems? So here's one way of doing this very briefly. I can say, let's take a polynomial that partitions the space nicely. We have our cells, and we have our weak bound that I didn't tell you how we proved, but they said it's easy. We now, instead of applying the weak bound on the entire configuration, we want to apply it separately in each of the cells. We're going to apply it separately in each of the cells. So if cell J, let's say it's contained m sub j points and intersected by n sub j lines, there should be j here also, then we apply this weak bound on the cell and we get this. And we sum this up over every cell. and we do some calculations, which I'll skip, and this leads to the summarized order bound. Again, we just partition the plane into cells, apply the weak bound in every cell, and we can, by some calculation, get to the summarized order bound. And to do this calculation, we need all sorts of basic properties of polynomials. For example, if I remove the zero set of a polynomial of degree r, how many cells can I expect to have? If I have, with lines it's a bit easy, but let's say I have some algebraic curves, how many cells do I expect the curve to be, to intersect? Which is, for a curve to pass from one cell to another, it has to intersect the partition. So this is actually kind of Bezout's theorem. And all sorts of other basic properties of polynomials, and you'll eventually get this bound. Now, it might look weird. Why would applying the weak bound separately in each cell help us in any way? I don't have a lot of time to talk about it, but here's a 30-second intuition. So we have this weak bound. You can think of it, we have endpoints. So an average point sort of contributes square root of n to the bound, right? An average point contributes square root of the number of lines to the total incidence bound. But if you apply the weak bound separately in each cell, an average point in the cell will only contribute square root of the number of lines that intersect this specific cell. And it's easy to show that in an average cell, the number of lines that intersect it is much smaller than n. It's going to be a lot smaller than n. So it's kind of, so this is a very brief intuition. We can talk about this a lot more for why this amplifies the weak bound, applying it separately in each cell. Okay, but I was lying a bit. This doesn't count the number of incidences. Okay, I went over each cell and asked how many incidences are in each cell, and I summed them up. But there are more incidences. Where are they? There are incidences that are in none of the cells. For example, look at this point. It's on the partition. So when I'm throwing away the zero set of the polynomial, it goes away, and I miss this incidence. So there are incidences on the partition, and we need to handle this. But actually, in this planar case, it's really simple. All you have to do, I'm not going to do it, you just look separately at regular and singular points of the partition, and it's very easy to do. So that's not a big issue. But let's do a brief recap. What did we do here? How did we use the polynomial method? We started with a weak incidence bound that's very easy to get, and was known way before. We partitioned the space into cells using polynomial partitioning, and we amplified the weak bound by applying it in every cell separately. At the end, we also need to count incidences on the partition, but it's not the main issue here. Okay, so where's the problem? Why are there so many different papers that do this more improvements and more dimensions, etc.? Because once we go out from the plane to higher dimensions, there's a big problem. There's a serious problem that's the main difficulty in deriving such theorems. Now the partition is quite complicated. Let's say we're in 3 dimensions. We have a set of planes. We have a set of points, planes, say, and we do the partition. We can get the weak incidence bound. We can apply the weak incidence bound in each cell. All of this works great. There's no issue. The issue is how to handle the incidences on the partition. The partition can be a very high degree variety. I mean, we have a bound for the degree, but it can still be very high. And each plane can intersect the variety in a very complicated curve, also high degree. And most of the points can be on this variety. So we just have an incidence problem that's a bit more complicated than the one we started with. Okay. So how do we handle incidences in higher dimensions? One way is this approach. Let's call our partition S1. So after dealing with the cells in the standard way, we still have incidences on a d-1 dimensional variety, right? Incidences that are on this d-1 dimensional variety V. What we're going to do is we're going to take a second partition. This partition is going to partition not the space, but the first partition. It's going to partition our variety S1 into cells, such that none of these cells contains many points. Okay, but we're not done, because if we did this, it's possible that most of the points are on the intersection of these two varieties, which is a d-2 dimensional variety. So you can see where this is going. Then we need the third one and the fourth one, etc. So it will look, okay, third one, fine. It will look like this. After J partitionings, we still need to handle an incidence problem where we have points on a d minus j dimensional variety. So what we need is a theorem that looks like this. We want to have, we're given a variety, v sub j, I'll just call it v, and we wish to find a polynomial f that satisfies the following thing. There are points on v, and f should be an R partitioning for the points on this variety. Should partition it into cells so that no cell contains too many points. We should be careful that f does not contain v, because if f contains v, there are no cells. We throw away f, we throw away the entire variety, all of the cells are empty, so it's okay, but we didn't do anything. So we need to be careful that it does not contain v, and we still need to bound the degree of our polynomial so that it's not too large. So think of what happened here. We started with a very combinatorial problem, and now we got to proving this result, which is really not a combinatorial result, maybe an algebraic geometry result, I don't know. So we got a very different type of problem. How are we solving this? So I can't solve this because I didn't even show you yet how to do an R partitioning of the space before we even get to an R partitioning of a specific polynomial, right? Of a specific variety. So let me remind you, the Good-Katz theorem for partitioning a space was for every parameter R, every set of points, there always exists an R partitioning polynomial. A polynomial of degree not too large, linear in R, that partitions the space such that no cell contains too many points in it. Okay. How do you prove such a thing? So to do it, let me just define it. I'm going to say that a hyperplane or something else bisects a point set if each of the half planes, half spaces, in this case half planes, contains at most half of the original points of the original sets. Okay, so our goal would be to build a partition in an iterative way. Let's say that, let's say we have this case of 19 points, and let's say R is 3. So I need every cell to contain at most m over R squared points, which in this case is 2. So every cell should contain at most 2 points. So first thing, I just want to bisect my point set. So maybe I bisected it like this. Okay. Now I have 2 point sets. I want to simultaneously bisect both point sets, maybe like this. Now I have 4 point sets. I want to simultaneously bisect all 4. So maybe like this. Okay. Great. So I have a strategy, but it's really non-rigorous and non-technical. I didn't tell you how to really do it. I just said we're going to do it iteratively. Each time we have a lot of point sets, we want to simultaneously bisect them all, and we'll keep doing it until the cells are small enough, contain as few points as we need. How do we do such a thing? So, if you know the ham sandwich theorem, maybe it will reminded you of it, because the ham sandwich theorem says the following. If we're in a d-dimensional space, and we have these sets of points, maybe the yellows and the blues here, there always is a hyperplane that simultaneously bisects all d of them. So this is the 2-dimensional case. And this looks like what we need, right? We want to bisect several point sets. We can use a ham sandwich theorem and bisect this set simultaneously. But there's a problem. It only works up to these sets. And I'm going to get to a lot more than d. So we can do the first log these steps, fine. But this is really a small number. We're going to usually want a lot more steps than this. So what do? So here's one way of doing this. We're going to start, we have k sets of points in a d-dimensional space. We want to simultaneously bisect all k somehow. If k is small at most d, we can use the ham sandwich theorem, no problem. What if k is larger? Then we're going to use the Veronese Map. What's the Veronese Map? So it basically takes coordinates of a point from some space to all of the monomials in these coordinates up to at most some degree. If you're not familiar with it, I think the best way is to look at an example. So here I have a Veronese Map. It takes 2 coordinates, so a point from the plane, and maps it to all of the coordinates of the monomials in these coordinates of degree at most 2. So there are 5 in this case. If I wanted more coordinates, I can map it to all of the monomials of degree at most 3 or 4 or whatever, and get more and more monomials. And that's what I want. I want to get to a sufficiently high dimensional space. I think I'll skip the technical details here. But the point is, if I have k sets to bisect, I want to go to a dimension that's at least k dimensional, to a space that's at least k dimensional. So I just need to, let's say that capital D is the degree of our monomial. I just need to take capital D to be sufficiently large, so there are enough monomials of degree at most capital D, at least k, so we'll go to at least a k-dimensional space. And why is this good? Because then we can apply the ham sandwich theorem. Once we map our points to a sufficiently high-dimensional space using the Veronese map, we can use the ham sandwich theorem and find a bisecting hyperplane. So again, we started with point sets. Use the Veronese map to go to a sufficiently high-dimensional space. So instead of p's, I'm calling these p primes, and I mean my higher dimensional space. And then I'm allowed to use the ham sandwich theorem because now the dimension is at least as large as k, and I have a hyperplane that simultaneously bisects them all. And you might say, okay, you bisected the wrong sets. We wanted to bisect the p's. Well, we now bisected the p primes, but you can probably already guess what we're going to do next. We're going to pull this back to a lower dimensional space. So we're going to sort of think of it as the inverse of the Veronese map and see what happens to our hyperplane H. And intuitively think about it like this. H is defined by a linear equation, right? Linear in the parameters of the higher dimensional space. But what the Veronese map did is it mapped a monomial of degree at most capital D to each coordinate. So I can think of each coordinate, instead of being a coordinate in the higher dimensional space, a monomial in the original coordinates of degree at most capital D. So H, by pulling it down, goes to a variety of degree at most capital D. So, okay, what else? You can probably guess what it does. It also bisects the point sets, the original point sets. It's very easy to show because the hyperplane bisects the p primes. When we go back down, this variety bisects the original point sets. Again, I'm skipping so many details and so many issues. I'm just going to show you the very basic idea here.
Sorry, can you say again how were the p primes related to the p's?
Yes. What we did is we used a Veronese map. So a Veronese map,
That I've got.
okay,
I'm
sorry.
used to that guy.
So let's say that MD is just
Just the image under the set. Just the image of pi.
oh
under
yes,
the
yes, sorry,
Veronese
yes. So you knew the answer, you didn't need me. Yes, you just applied the Veronese map on the point sets. That's all we did. Okay, we're here already. Okay, so by doing this trick, using Veronese map and then ham sandwich theorem, we can bisect point sets as much as we like. Not only I skipped a million details, I didn't even check what degree it gives me. What's capital D, how large can it be, and what polynomial degree I get eventually, but it all works. It gives a nice polynomial partitioning. I'm skipping all the technical details today. Okay, but we actually wanted to prove something a lot more general. We wanted to prove not a partition of the space, but a partition of a specific variety. This is what we wanted to prove. A polynomial that partitions points on a specific variety without containing this variety and still having a nice degree. How do we do this? So actually originally we had a very complicated proof, but now we have a much simpler argument. Let me quickly show you how it works. And this is the more technical part. I assume some people who are not that familiar with this will lose me, but that's okay. It will briefly be over. And then we'll move to a different problem. Okay, so I'm going to define this, the polynomial ring subset at most, subscript at most d, as the subset of the polynomial ring of polynomials of degree at most capital D. And similarly, if I have my variety V that I want to partition, let's say that I is the ideal of all polynomials that vanish from this variety. So I'm going to do I subscript at most D be the subset of the ideal of all the polynomials of degree at most capital D. Just two subsets. And the important object here is R, the quotient of the subset of the polynomial ring and the subset of the ideal. And the idea is, we want to, for a polynomial partition, we will only consider polynomials in this quotient. And this already helps us a lot because, well, we lose some redundancy. Every polynomial has a different behavior in V here. But also, the only polynomial that vanishes on V is the identity. So as long as we don't take the identity from here, we know that our polynomial cannot vanish on V. Great, so now we proved one property that we want for our polynomial. It does not vanish on V, but I'm sure this doesn't impress you that I know how to solve the problem of getting a variety and finding a polynomial that does not vanish on it. Let's move on to the more difficult stuff. Now, we somehow have to do a partition. There are point sets on our variety V, and we want to partition it into cells somehow. So, what we want to do, as I said, we want to take only polynomials from our quotient, and I want to repeat the argument of the Veronese Map, but I can't. I have to do a similar fake Veronese Map. So, instead of looking at all monomials of degree at most capital D, I'll look at the elements of the basis of my quotient, and I'm going to map to this basis. So if the Veronese map went to the basis of all of the polynomials, this is just the basis of the polynomials in my quotient. So it goes to a lower dimensional space, but still it goes to a higher dimensional space. And I'm going to do exactly the same. It's the same thing. I have k point sets on my variety. I'm using the fake Veronese map to take them into point sets in a higher dimensional space. In the higher dimensional space, there's a hyperplane that simultaneously bisects them, and then I can pull it back down and get a polynomial that partitions everything. So again, there are a million small details, but I just want to show you the basic idea of what's happening here, so I'm going to skip them completely. And so good, now we have a polynomial that's an R partitioning of the points of our variety, and does not vanish on it. But how can we find out what degree it has? So finding how many how many monomials of degree at most D there are, it's pretty simple. How do you find how many elements are in the basis of our quotient? And that's where we use the Hilbert function. Hilbert function, if you don't know, it's a polynomial of degree 37 with zeros that looks suspiciously like Hilbert. I apologize. I had an urge to put this here. Okay, Hilbert's function, the real definition, if we take I to be the ideal of all the polynomials that vanish on a variety, is defined like this. It's a function, takes capital D, and gives us back the dimension of the same quotient as we defined. It's exactly the same element. So it's exactly what we've been looking for. If you want to see to what, if I need to go to a k-dimensional space, to what degree of capital D I need to go to, it's exactly the value of the Hilbert function. But that doesn't mean anything. I just gave it a different name, right? It's so instead of the degree of the dimension of my space, it's the Hilbert function. But Hilbert functions obviously have been studied a lot. We know a lot of them, and I'm going to skip completely how we do it. But very basic properties of Hilbert polynomials, Hilbert functions. You can show that to get to a k-dimensional space, you need to go to polynomials of degree about this size. Again, it shouldn't tell you anything. It's just
This is just the Riemann-Roch theorem, right?
you don't even need to use any heavy theory. Yes, I mean it's just basic properties of Hilbert polynomial. Don't need to go there.
Because you're always putting, okay, so this is a basic construction in algebraic geometry. So it doesn't have to be in Euclidean space at all. I think the only Euclidean space thing is this Ham-Sandwich theorem. But everything else is just, you're looking at sections of a certain line bundle and mapping into the space of sections. That's what this
Right.
is.
Actually, the Ham-Sandwich, it's also not that tricky. It uses Borsuk-Ulam as long as it's a simple argument that will work in a lot of cases. So yes, you could probably do it in many general cases. I should say, people are studying incidence problems in all sorts of more restricted cases. For example, this proof in our paper, we have a lot more results that are highly completely. One of them is that it works for semi-algebraic or definable varieties. The same proof more or less works. And very recently, this month, people extended the similar ideas to get results in all minimal frameworks. I guess all sorts of people who work on model theory, they're trying to generalize all sorts of things to more general models. Okay. So, well, I need so many details from you, but we're more or less done. By doing this we got what we wanted. We can do multiple partitionings and we can get incidences in any dimension. Again, I'm sure this is not completely satisfying because I skipped so much, but I just wanted to give you the basic idea of what's happening. And I see I have some more time, which is great. Let me talk about a different approach for incidence problems. This was very algebraic, right? So, Veronese and Tao, a few years ago, they generalized summary trotter to a complex plane. What they did, they said we have m complex points and complex lines. We can get more or less the same as summary trotter again, except that we have this annoying extra epsilon. Actually, following works also remove this epsilon, but never mind. But their approach was really specific to lines. Theoretically, they wrote it in a general way, so you can apply to other things, but really, lines are the only natural curves that I know of that actually satisfy the restrictions.
These are complex lines again?
Yes. Yes. And another thing we recently managed to do, this is with the geometry called Sabo, and again my collaborator Zal, is we managed to get this more general result. They stated that this holds for the real plane before, and we managed to get it to the complex planes. The first general complex incidence bound have m points and complex curves, no KST, and the same bound. Now, why does it require different work? Why are all these works? What doesn't work in complex? So something very basic fails first. A polynomial does not partition the complex plane into cells, right? You take the zero set of the polynomial and you remove it from the complex plane. You don't get cells. You just get most of one big connected component minus some small piece that you removed, right? So we cannot use this approach, but we can do something very similar by just thinking of the plane as R4. The complex plane is R4. Each two complex coordinates, each complex coordinate, we can think of it as two real coordinates. And we get a similar problem. Now, our complex curves become two-dimensional varieties in R4. Our points remain points. And we can apply a partitioning polynomial here, and we can get a weak bound, apply the weak bound separately in each cell. Everything is just as always. But there's still a problem. If it would work, we wouldn't need the paper by Veronese and Tao, and we wouldn't need this. The problem is, now we have a three-dimensional variety V, that's a partition, and we need to handle the incidences that are on this partition. And the hard part is to handle incidences between points in this partition and two-dimensional varieties that are fully in this partition. And actually, if this was the problem, we wouldn't know how to solve it properly. You can use the tools we've just seen, all these multiple partitions, and it would work. It would just give you a worse bound, not the bound that we want, not the bound that we have in the plane. To get something better, we need to do something more sophisticated. And luckily, these are not arbitrary two-dimensional varieties, which we wouldn't know how to handle. They have very special properties. They originate from curves in C2. And specifically, these two gentlemen here hint you what we're going to use. Because they originate from curves in C2, they satisfy the Cauchy-Riemann equations. Now, I'm not sure if I should say what the Cauchy-Riemann equations are not here. I think I should just skip it. I hope that if somebody wants me, just tell me. So even though they're in R4, they obviously still satisfy the Cauchy-Riemann equation. Let's see. Okay. So we have a three-dimensional variety V, and we need to handle incidences between points in this variety and two-dimensional varieties that are fully contained in it. And you can use the Cauchy-Riemann equations to say, I'm skipping a few steps, of course, but you can say for a generic point in the variety V, if we have a two-dimensional, we can associate with this point a two-dimensional plane, such that every two-dimensional variety that passes through this point will have this plane tangent to it. This will be its tangent plane. So in particular, if several of a two-dimensional variety meet in the same point, they will have the same tangent plane there. And there's a very simple explanation for this, intuitive explanation. Think of two curves in C2. and say that they have a common point. Either that they're tangent at this point, or they intersect fully in this point. If they're tangent, then they have the same tangent line, or in R4, the same tangent plane. If they're transverse, then it means they're two complex lines, tangent line intersecting a point, which would mean that they're two-dimensional planes intersecting a point. But that's a problem. Two-dimensional planes that intersect in a point span the entire space. And don't forget that they're actually in a three-dimensional V. So the tangent of V it's a hyperplane, and it should contain two-dimensional planes, but it cannot because they span the entire space. So this cannot happen. If two things meet in a generic point, a singular point you can have, it can still happen, they will have the same tangent plane. Okay. So what? So let's see. We have a three-dimensional variety, points and two-dimensional varieties in it, and this can be thought of as an initial value problem. Take a generic point. We know for every point around it exactly, if something passes through it, we know exactly how its tangent plane looks like, or in other words, we know exactly how its first partial derivatives look like. So it's exactly an initial problem, an initial value problem, and that means that we can apply the Picard-Lindelof theorem, which tells us that in such a situation, there's a unique solution to such an initial value problem. What is a unique solution? It tells you that if you have a generic point in our variety, and there is a two-dimensional variety that passes through it, it's unique. There cannot be more than one, because we can define it uniquely using this initial value problem. And that means that through almost every point in V, there is at most one incidence. There are hardly any incidences on the partition, so we don't need to worry about what's happening in the partition. Intuitively, what's happening here is that this should be a foliation. We have our three-dimensional variety in R4, and we have the two-dimensional things contained in it, and if they can hardly ever meet. They can only meet in some singular points, so they basically foliate if they're there. Okay, theoretically, there might not be any two-dimensional varieties in this. Okay.
People like in dynamics would know that as a lamination. If you don't foliate at every point, it's a lamination.
I should update the paper, I guess. Okay, so that's more or less what I wanted to say. I hope that maybe I convinced someone here that incidences are something interesting. I believe that we'll keep seeing them appearing more and more in the future, but I guess we'll see. Thank you very much.
Any questions?
Maybe one strange thing about this Veronese map.
Mm-hmm.
When you write it from a Euclidean space like that, you really map points to points, but at least in the algebraic geometry level, you really want to think about mapping points into the projective space of the section, so lines. Is there, I mean, maybe that doesn't really change dynamics, but is there any algebraic geometric interpretation of these things?
So if I understood the question correctly, so you can just think of a projective incidence problem. You don't have to be in a defined space, right? And I guess that's what it will correspond to, which is more or less the same. You can just do a projective translation that takes all of the points out of infinity and get to a defined problem. So it's not really any new information, I think.
So at the start of the talk you mentioned, say, finite fields. Does any of this sort of work over in that realm?
So in finite fields, the main issue is that you have no such partition. It's not clear how to partition, right? So the bounds are much worse because of that. The bound Summer-Trotter, I told you, there's a very easy combinatorial argument that gives you m square root of n. The best known bound is not too far from this. It's just a bit better than this. And it's a very difficult set of problems, and there's a lot of work on it. But different tools, of course.
I guess what I was trying to say before is not really a question. It's more like a statement.
Yes.
So suppose that you were throwing your points not in all of Rn. But you already started with some hypersurface, and you want to throw them only on that. Then these ideas would give you, I think, better bounds. If you knew something about that variety, if you knew something about how many sections
I see.
it had. Anyway.
Yeah, that's an interesting thing. We can talk about this now later. Thanks.
Okay, thanks, Steve.